Did we have tea spillage again? That's good. Bonus quiz 3 is up. If you can't print on legal size paper, give me a holler and I'll print a copy of this for you. You'll find out that some of the questions on bonus quiz 3 relate to chemistry of graphite, which we've already discussed, and also provides a foundation, at least this is my intention, for a strong springboard into organic chemistry. You'll see what I mean when you look at it. Or if you've looked at it, you've already seen what I mean. And then some questions on stuff we are presently considering. Now, we jump. Section 24.2 in chapter 24, which is on page 24.2. And consider in brief the work of Alfred Werner. This goes back to the late 1800s, early 1900s. This guy's often referred to as the father of inorganic chemistry. Prior to Werner's work, and other people who worked at the same time as Werner, practically speaking, there are only two disciplines of chemistry: physical and organic. There wasn't a whole lot at the time at which Werner did this work. Not a whole lot of recorded work regarding what we now consider to be inorganic chemistry as opposed to organic chemistry. Simply put, what you probably now know is organic chemistry is the study of molecules, each of which contains at least one carbon-hydrogen bond. But there are a number of other molecules which are also considered in organic chemistry, in which you'll find no carbon-hydrogen bonds, simply because carbon is the principal skeletal atom of these molecules, like carbon tetrachloride, an obvious derivative of methane, CH4. Operate on it, turn it into CCl4. Furthermore, the particular work of Werner with which we are concerned, given that it relates directly to chapter 24, is what did he do to provide a springboard into recognizing the coordination phenomenon, a mode of bonding which at the time Werner did this work had not yet been recognized, had not yet been thought about. Two experiments. A sample of cobalt-3 chloride dissolved in water. That's all he did. What did he observe? On dissolving the cobalt-3 chloride in water, a redox reaction occurred, as evidenced by the fact that this solution began to liberate oxygen. What happened to cobalt-3? Evaporation of the solution gave a compound with this formula composition. So Werner, even though back in the late 1800s had few technical methods of instrumentation and investigation, when per mole of cobalt you analyze this, you got 3 moles of chloride ion, and you run this reaction, you evaporate to get the solid product, what contains cobalt, and you now analyze and find you got 2 moles of chloride ion per mole of cobalt. I mean, even at that time, he was able to do investigations of this nature. What's going on? Well, in general, the chemistry for this first investigation is referred to by this statement here. Cobalt-3, water, because you can't reduce chloride ion. Now, I don't know if Werner knew that, but we know that. Chloride ion in a -1 oxidation state, that's the lowest achievable oxidation state for the halogen atoms. So it had to be cobalt-3 that's getting reduced. And obviously, by analysis of this material, the product of this reaction, you find out cobalt-3 got reduced to cobalt-2. Tell me, as this reaction runs, what happens to system pH? Is there a change in system pH? You bet there is. What is the change in system pH which also takes place during this redox reaction? You think we might have discussed stuff like this in the chapter 22 on electrochemistry? If you look at the table of half reactions, you think you can determine what happens to system pH? Look at the table of half reactions. See if you can find the half reaction to which we are referring. What half reaction are you looking for? You won't find any half reactions involving cobalt. But you will find half reactions involving water and oxygen, won't you? As water is oxidized to oxygen, what else do you produce? What? Hydronium ion. So system pH is coming down. So, we're in position to recognize such as a consequence of our work in chapter 22. But now let's go to the second experiment which Werner did, and really, which is the one which I believe triggered his thoughts about this thing called coordination chemistry. Who knows what may have been called in those days. Again, cobalt-3 being dissolved in water, but not now pure water. Instead, 6 molar ammonia. No oxygen liberation. No redox reaction. What's the difference? How come I get oxygen here and I don't get oxygen here? How come I get redox here and I don't get redox here? And to pursue this, after dissolving the cobalt-3 chloride in the 6 molar ammonia, he again evaporates the dryness to see what's the fate of cobalt in this second experiment, and gets a material of this composition. Cobalt's preserved in the +3 oxidation state. But now, along with cobalt and chloride ion, in the composition of this material, the material obtained by solution evaporation after experiment number 2, 6 moles of ammonia per mole of cobalt. Here, 6 moles of water per mole of cobalt. So, back to this result coupled with this result. You say, well, isn't this interesting? Because I know under normal laboratory conditions, water as a pure substance is liquid. At least principally. It's also vapor. And ammonia under normal laboratory conditions is a vapor phase stuff. So now he's producing 2 solids, one of which contains water and the other which contains ammonia. Interesting. So by coordinating water, you get to be in solid state under normal lab conditions rather than liquid state. By coordinating ammonia, you get it to be part of the solid state rather than vapor state. Hey, we've seen materials like this throughout. We've talked about this before. Remember considerations of the chemistry of this stuff by way of your work in 46 Laboratory Assignment 3, by way of what we did in Chapter 19 on equilibrium involving salts of limited solubility in water. I believe at that time we mentioned that. This is the principal component in a very common home construction material. What home construction material do I refer to? What is it?
Plaster of Paris.
Plaster of Paris is this. Solid, but per mole of calcium sulfate, on analyzing plaster of Paris, I find 1/2 mole of water. To turn this into a plaster cast, I add water to this and it converts to this. This is gypsum. This is the component of the common household building material to which I refer. Anybody know what this stuff is? You ever do any home construction work? You ever make walls? Plasterboard? Commonly called sheetrock. How many of you are familiar with that stuff? Sheetrock. Hey, that's the main ingredient in that. Well, you're familiar that sheetrock is not a material which cries, does it? You don't see the water molecules, liquid phase, falling out of this stuff. You'd hardly make walls out of this stuff at home if that's the way it behaved. That was just to remind you that we've seen stuff like this before in the chemistry which we have been discussing this term. Now back to this. So, Strain's observation number 1. How does the chemistry of this material cause water to be present in the solid state? The chemistry of this material causes ammonia to be present in the solid state. And why is it, for experiment number 2, where water is still the main component of this system, I don't get oxygen, I don't get any redox reaction? Werner concludes, now he doesn't at that time recognize for sure what the structure is, but he does conclude that somehow, some way, the ammonia molecules present in this system are preventing cobalt-3 from contact with water molecules. Because in order to make the oxygen, the only oxygen atom-containing stuff in the system is water. So if you're going to make oxygen, you have to oxidize water. And in the first case, it must be true that cobalt-2 is coming in contact with water. Whereas in the second case, even though the main component of the system is still water, water's not able to come in contact with cobalt-3 in the second case. What's going on? What's going on is coordination. Question. Based on Werner's results, here are 3 common Lewis bases, which you now know can also be named as ligands. Ligands, whatever. Okay. Which of these 3 appears to be the stronger ligand toward cobalt-3? If you have, from these results, if I now assign you the task of arranging these in order of relative Lewis base or ligand strength toward cobalt-3, how will you arrange them based on these results? Which one of these appears to make the strongest bonds with cobalt-3? Which appears to make the weakest bonds? Well, in the first investigation, did the chloride ion succeed in preventing water from attacking cobalt-3? No. In this investigation, did the ammonia molecules prevent water from contacting cobalt-3? You betcha. The results speak for themselves. So this causes us to recognize that ammonia certainly makes stronger bonds than water toward cobalt-3. Now we can't say for sure between these two, because when we evaporate this, it appears to be the case that per cobalt you get 6 waters. Like here, per cobalt you got 6 ammonias. But the composition of this tells us I can't get 6 chloride ions per cobalt. I don't have enough moles of chloride ion. So I can at least say that ammonia is making stronger bonds than water toward cobalt-3 from this investigation. So what might be the structure for this stuff, given that ammonia has not only shown itself to make stronger bonds with cobalt-3, how might the ammonia molecules be structurally related, arranged with respect to cobalt-3 in the composition of this stuff, to keep the water molecules from contacting cobalt-3? Hey. You get an octahedral complex. Now keep in mind, when we look at these models, these sticks are for our convenience to represent positions of bonds. You don't see these sticks when you look at actual molecules. If this simple sphere is simulating an ammonia molecule, and it's smushed right into the nitrogen end of the ammonia molecule's electron cloud is smushed right into the cobalt-3 electron cloud for orbital overlap and bond formation. So if you got 6 ammonia molecules wrapped around this thing which simulates cobalt-3 in an octahedral fashion, you now have no place in space where water molecules can get close enough to cobalt-3 to establish contact with cobalt-3. And if it can't, the water molecules can't contact the cobalt-3, then I can't get this redox reaction. Interesting. All right. Enough said then for the work of Werner. Let's look at more information, which tells us about the coordination phenomenon. We're now going to section 24.5 and take a look at the data which is contained in the table at the bottom of page 24.6. There are 4 compound formulas written in general formula representation. I've written these formulas in somewhat different form than you see in the table in the notes. I've written these formulas to keep with the way we wrote the formulas here for the Werner compounds. Because Werner in his day had no way to determine structure. He could determine composition, but he couldn't determine structure. Now you know I try to make a practice of writing formulas to keep with structure. So we're going to look at this collection of formulas, and then we're going to pay attention to the data. One column of which represents conductivity of a mole of this compound dissolved in water. And per mole of each of these compounds dissolved in water, how many moles of chloride ion can I readily precipitate by treating that solution, a mole of each of these compounds, with excess silver nitrate solution? Because I know free-floating chloride ion in water solution, silver ion added, boing, silver chloride falls out. And after we consider these data and let the data talk to us, then we're going to rewrite these formulas. We're going to rewrite these formulas to show structure And we will rewrite the formulas so as to follow the general rule that a complex has its formula contained in brackets. You recall how I've written the formula, for example, for nickel tetracarbonyl and the other complexes which we were talking about at the end of chapter 23, the conversation of which we finished yesterday? The complex, after its composition has been identified, has its formula written inside brackets. So we're looking at a bunch of compounds, each of which contain octahedral complexes of platinum-4. By examining this information, we'll write the formulas for these octahedral complexes, and I'm taking the information on platinum-4 forming octahedral complexes as a given, because in light of today's knowledge of chemistry about platinum-4 and a whole bunch of other transition metal ions, we know now that platinum-4 in its coordination chemistry forms octahedral complexes, period. Never forms tetrahedral, never forms square planar, never forms any other geometry. Just octahedral. Interesting. Well then, 1 mole of this, 6 moles of ammonia, 4 moles of chloride ion. Dissolve a mole of this in water and observe conductivity. In so doing, we discover, as the information shows, 5 moles of ions per mole of compound. And if this solution, prepared by dissolving a mole of this compound, mole of this compound dissolved in water treated with excess silver nitrate solution, gives ready precipitation of 4 moles of silver chloride. Now, before we start talking about structure for complex, let's take a peek at compound number 2. What's the difference? Both have a mole of platinum in the +4 oxidation state, both have 4 moles of chloride ion, and both have an abundance of ammonia molecules in the composition, except this has 5 moles per mole of platinum, this has 6 moles per mole of platinum, and we see a difference in conductivity, solution conductivity, as well as moles of readily precipitatable silver chloride. Here, 4 moles of ions per mole of compound and only 3 moles of silver chloride readily precipitatable. Now we got information to make decisions on complex composition and structure, given that we are starting with the given statement that platinum-4 forms exclusively octahedral complexes. So we're going to draw this picture. You see what I'm drawing? Here's what I'm drawing. Now, I can pull off all the white spheres because they simulate ligands. And then what we'll see is this. Stick up top is representing the bond, the coordinate covalent bond that connects platinum-4 to the topmost ligand. Stick at the bottom, right here. Simulates the coordinate covalent bond involving platinum-4 to the ligand at the bottom of this octahedral complex. If you want to draw sticks here, but I don't think that's necessary, I think it just complicates the diagram, you would simulate this stick, this stick, this stick, and this stick, each of which together simulate the square planar part of each and every octahedral complex. Now, I think you learned in Chemistry 2045 the language axial and equatorial. Did you learn that language? Axial. The top and bottom atoms in conjunction with the central atom, which is platinum-4 here, Simulate an axis on which an octahedral complex can be rotated. What's rotating? This equatorial square plane. Because when I rotate like this, these atoms all wind up being recognized as part of the equator of this three-dimensional object. So we'll refer to the ligands in this square plane as equatorial atoms or ligands, molecules, whatever they might be. And again, this is a three-dimensional figure. So we have a challenge before us. We have to be clever in our artwork to try to draw a reasonable picture of a three-dimensional object on a two-dimensional drawing surface. So to do that, I draw what's called a canted square, like this. Not very good. But not like this. Because this would represent a square that's in the plane of the drawing surface. Whereas the canted square means we're looking at a square which is perpendicular to the drawing surface. These two front corners of the square are out in front of the drawing surface. Here's the drawing surface, and these two atoms or ligands or groups, whatever they might be, are part of that portion of this equatorial square which is behind the drawing surface. These are behind the drawing surface. These are in front of the drawing surface. That tells you how to interpret this picture. It tells you how to recognize what this picture is attempting to show you. Okay? Now then, compound number 1. 5 moles of ions per mole of compound. Well, the ionic components of this thing are platinum 4 and 4 chloride ions. So it must be true that the complex contained in compound number 1. Well, I've already drawn it here. Why should I bother drawing this thing again? Let's just take this thing and call it platinum 4. Must be this. So since we're going to wrap brackets around the formula for the complex, I'll wrap brackets around this Lewis picture for the complex and put a charge of plus 4 because the ammonia molecules are neutral. So the overall electric charge on this complex is still plus 4, keeping with the plus 4 oxidation state of platinum. And all the chloride ions are in the solid state ionically bound. Well, what do ionic compounds do when you dissolve them in water? We've been through this way back when? Way back at the start of the term. What do ionic compounds always do when they're dissolved in water? They dissociate into their component ions. Well, what are the component ions of which this compound is composed? Chloride ions and this ionic complex. So, I put a mole of this in solution. I got 1 mole of this floating around and 4 moles of these. That's 5 moles of ions. There's the 5 moles of ions found per mole of compound found by conductivity investigations. And since these chloride ions are floating around free in solution, not bound to platinum 4, when I treat a water solution of this with excess silver nitrate, all of these readily turn into silver chloride. There we have it. Now we go to compound number 2. Now I don't have enough ammonia molecules per mole of platinum 4 to surround all platinum 4 ions in the system with 6 ammonia molecules. The best I can do is this. It doesn't make any difference which of the ammonia molecules I erase from this first coordination sphere. That's just fancy language identifying these ligands or Lewis bases which are directly coordinated to the central metal atom or ion. Okay? So one of these coordination positions in compound number 2 has got to be occupied by a chloride ion. Because if this other coordination position wasn't occupied, this thing wouldn't be octahedral. It'd be trigonal bipyramidal. And since I still have 4 moles total of chloride ion for compound number 2, I now know I got 1 mole of chloride ion coordinated and 3 moles of chloride ion for free floating. That gives me now a complex whose charge is +3. It gives me a compound which gives me 1, 2, 3, 4 moles of ions per mole of compound. That keeps with the conductivity investigation result. And I now have 3 moles of free floating chloride ions, which means I'll be able to readily precipitate 3 moles of silver chloride as opposed to 4. So, there's compound number 2. And now we can answer this question. In this case, at least for platinum 4, how does the strength of ammonia molecule as a ligand toward platinum 4 stack up to chloride ion? Ammonia's got to be stronger. Otherwise, these chloride ions would all be in the first coordination sphere. And we wouldn't have composition formulas showing us all these moles of ammonia. Now then, we go to compound number 3. Here, the number of coordinated ammonia molecules has again been reduced. And the number of moles of ions per mole of compound has been reduced. So I think now we can readily recognize that for compound number 3, we've got a complex in which per mole of platinum 4, we got 4 moles of coordinated ammonia and 2 moles of coordinated chloride ion. And an additional 2 moles of ionically bound chloride ion, which then become free-floating chloride ions when I dissolve a mole of this compound number 3 in water solution. So those 2 moles of free-floating chloride ions are readily precipitated when I treat with excess silver nitrate solution. But I don't precipitate the chloride ions which are coordinated, because those are quite stable chloride ions. Question: does it make a difference when I put that second chloride ion in the structure of this complex? Does it make a difference where I put it? So when we're looking at complex number 2, if the purple thing simulates a chloride ion that's coordinated, and the silver part is the platinum 4 central metal, and the 5 white spheres simulate the 5 ammonia molecules that are coordinated, when I go from complex number 2 to complex number 3, which I do by taking away 1 more ammonia molecule from the first coordination sphere and replacing it with a chloride ion, does it matter where I put the chloride ion? Well, if this ammonia molecule goes away, then the chloride ion goes there, and I have chloride ions in the first coordination sphere which are separated from each other by a 90-degree angle. On the other hand, if instead this ammonia molecule went away and was replaced by a chloride ion, then I'd have a complex with this structure, where now the 2 chloride ions in this first coordination sphere are at a 180-degree angle from each other, and as far apart from each other as they can get in this first coordination sphere. So let's draw pictures of these on the board and answer the question, how can we distinguish between these complexes by language, by nomenclature? The N's mean, of course, ammonia molecules. Here are the chloride ions at 180 degrees with respect to each other. They could each be here and here, or here and here. I've shown them here and here. As opposed to, say, here and here. These are chloride ions at a 90-degree angle with respect to each other. The language is Trans versus cis. If you read the information about this in the notes, you've already seen this. Trans simply means opposite from each other, across from each other, as far apart from each other as they can be. For this case, it's a 180-degree angle with respect to each other. Cis means as close to each other as possible. And recall, perfect octahedral geometry is really a simple geometry, even though you got 6 peripheral atoms. It's a simpler geometry than trigonal bipyramid, where you got 5 peripheral atoms. Because for trigonal bipyramid, you got 3 principal bond angles. 90, 120, 180. Here you only got 2. 90 or 180, that's it. No other possibilities exist for a perfectly octahedral geometry. So cis means 90-degree angle and as close to each other as possible. Trans, opposite from each other. Far from each other as possible. 180-degree bond angle if we're talking about octahedral. Now, look at compound number 4, pardon me. Well, given that we've recognized from these studies that ammonia makes stronger coordinate covalent bonds to platinum-4 than does chloride ion, if we have ligand competition between ammonia and chloride ion, with the metal ion being platinum-4, we'll always expect the ammonia molecules to be coordinated. But when I get to compound number 4, per mole of platinum-4, I only got 1 mole of ammonia molecule. So, this will simulate the complex contained in compound number 4. What's the charge on this complex? Remember, the coordinated metal is platinum in the +4 oxidation state. And each chloride ion ligand bears a charge of -1. We got 5 of them connected to platinum-4. So what's the charge on the complex? -1. So, when this compound number 4 is dissolved in water, beside a mole of this platinum-containing anion complex going in solution, I now also have a mole of K+ going in solution. That accounts for the 2 moles of ions per mole of compound. But now notice, when I treat a water solution of this with excess silver nitrate, I'm not getting any silver chloride to readily form, because all the chloride ions are stabilized by being coordinated to platinum-4. So one difference, of course, among others, that we've seen for the complex contained in compound number 4 is that this complex is anionic. Now you will recognize, when you look at the nomenclature stuff, I'm not going to pay a whole lot of attention to the nomenclature stuff. We could learn the rules. And as we look at these materials, I will often name them by their correct IUPAC name. But I'm not all that concerned with you taking time to learn the names of this stuff. But if you see a complex which contains 8, ATE, as the suffix at the end of its name, that means you're looking at an anionic complex. We'll exhibit such by looking at a couple of names. This thing here, this one right here. 1 mole of coordinated chloride ion, 5 moles of coordinated ammonia molecules. This is platinum-4. Pentamine. or pentamino, actually. Go in there. Monochlorochloride. All this is one big long word, and that's the name of the complex. Formula? Complex, formula contained in brackets. These outside the brackets means they are strictly ionically bonded. They're not coordinated. Now, this thing. If I want to now name compound 4, how will I name it? Well, before we write its name, let's write the formula for the compound, given that we now know the composition of its complex. There's the complex. So if I want to name this thing, first I recognize it's a potassium salt. Potassium. Amine or amino. Pentachloro. Platinate. 4. When you write names for these things, and the things we're naming contain transition metals, we're obligated to identify the oxidation state with cap Roman numerals. Because remember, these transition metals show considerable variation in their oxidation state. So to keep things nice and tidy, we include the oxidation state in parentheses. And here we see the difference. Platinate means this is an anionic complex. Versus maintenance of the name of the metal itself. This is platinum 4. Platinate 4. Again, no. I'm not going to make a big deal out of this nomenclature stuff. If I ask you anything on the final about nomenclature, it won't be worth more than a few points. Probably won't even do that. What counts most are formulas. So, if we have this information before us, I find this information to be far more valuable than this information. All right. Now then, let's go one step further with these platinum complexes, which contain chloride ion as well as ammonia molecule ligands. We're going to add another compound to our list. Compound number 5. PtCl3 PtCl4, pardon me, with 3 moles of ammonia per mole of platinum. Now, when we were playing this game and went from compound 1 to compound 2, we recognize in compound 2 there are 2 distinctly different coordination positions occupiable by the chloride ion ligands, which of course means as a group of ligands there are 2 distinctly different coordination positions occupiable by the group of 4 ammonia molecule ligands. The distinction being the chloride ions could be trans, as we had with this model, or cis, with this other chloride ion being up here, or over here, or over here, or down here. Those are all cis positions relative to this coordinated chloride ion. All right? Now we're going to the platinum 4 octahedral complex, in which we have 3 moles of ammonia coordinated. So by default, that tells us we've got 3 moles of chloride ion coordinated, because you've got to have 6 monodentate ligands in that first coordination sphere in order to define our octahedron. How about that? Now, when you see this complex from a cis-trans standpoint, how do the chloride ions relate to each other geometrically? Well, let's take our model and put in another chloride ion. While, of course, removing an ammonia molecule. You see this? Look at the model. Is this model this thing? Here's the model. Is this model the structure we have on the board? It isn't, is it? Because the structure we have on the board shows all the chloride ions geometrically related to each other by being at 90-degree angles exclusively. So, what I'm going to do is reposition the ammonia molecules and chloride ion ligands so that they're like this. You see now that all these chloride ions and all these ammonia molecules are strictly cis with respect to each other? 90-degree angles. This is what we got on the board. I'm pretty sure you've seen this model before. What is this? Have you not seen this before? Did you see this in 2045? This is a solid state model of an octahedron. Here's the ball and stick model. 6 ligands. Here's the solid state model. Ligand position up here, ligand position down here. Those are the axial positions if I hold the model like this. And 1, 2, 3, 4 apical positions which are part of the equatorial plane of this solid state model if I hold a model like this. Okay? So note, if I have the 3 like ligands in this octahedral complex oriented such that they're exclusively cis to each other, and I examine this with the solid state model, then I got a ligand here, a ligand here, and a ligand here. Ligand here, ligand here, ligand here. Octa. 8. What does hedron mean? Face. This octahedron is an 8-faced object. And a perfect octahedron has as a face a perfect equilateral triangle. Right? Okay? 8 perfect equilateral triangles constitute the 8 faces of a perfect octahedron. 6 coordination positions, 6 apices. So note, if like ligands, when there are 3, are all cis, they're all on the same face. Okay, so far? Now let's look at what we had shown you before. An array of like ligands which shows these cis to each other, like these, but these are trans to each other. This creates a nomenclature problem. The cis-trans language falls apart when we have this kind of geometry and structure shown by an octahedral complex, when in the first coordination sphere you have two sets of three like ligands. Well, let's go back to the solid state model. When the two sets of three like ligands are arranged like this, cis as well as trans to each other. Notice that when I look at the apices of the solid state model, for this arrangement of like ligands, I'll have a given ligand here, another ligand exactly the same as this one here, doesn't have to be here, it could be here, and the other one down here. This one and this one trans, this one cis, this one cis, but these two trans. Now then, this is a very regular three-dimensional object. It can be inscribed in a sphere. Do you believe that? That if I place this inside a sphere which has a radius equal to any one of these bond lengths from the central atom to any of our ligands, this bond length, I'm going to have a sphere which contains this octahedron, and every like ligand will touch the outer surface of the sphere. And if I see the three like ligands oriented at these three outer surface positions, then I can recognize these three like ligands will be all contained in a circle. If I draw a circle around the sphere like this, draw a circle around the sphere like this. Okay? Now then, if I draw a circle around the Earth that goes around the middle of the Earth, what have I drawn? Have I drawn an equator? Does it have to be an equator? No. It can also be called a meridian. A meridian is, with respect to Earth, any circular construction that goes around the surface of the Earth at a distance from the surface that's equal to the radius of the Earth. And all that fancy story relates to how I distinguish between this complex with two sets of three like ligands, cis as well as trans to each other, versus this complex with two sets of three like ligands, where all like ligands are on the same face. That's this. This is said to be facial because all the like ligands are contained on the same face of the octahedron. As opposed to, let's use this picture. These two chloride ions trans, these cis, these ammonia molecules trans, these two cis, these two cis. Meridian. Now I can distinguish between these things with names. So I'm going to call this thing platinum 4. Pardon me. This thing. Facial. Platinum 4. Trichloro. Triamino. Or triamino trichloro. I don't care the order in which these like ligands are named. There's rules about this. I think these are silly rules. I don't bother with those rules. As opposed to that, which would be meridional, platinum 4, trichloro, triamino. And then whatever the anion is. chloride, sulfate, whatever it is. Language. Now then, that brings us to recognize as a general and very important category of complexes the category known as isomers. In our case, let's put TM in there. Isomers of transition metal complexes. Two types. One, structural. Two, geometric. Nope. Stereo. And for stereoisomers, there are two subcategories. Geometric or optical. We'll talk more about those when we get there. Let's take a look at the structural isomers first. Structural complexes. Are of the same geometry but of different metal to ligand bond structure. So let's take a look at one type of structural isomer, which you will see relates to one of the questions on bonus quiz 3. Consider a ionization isomers. Examples of structural isomers. First, we write the formula. For a complex, an octahedral complex of cobalt, and a second octahedral complex of cobalt, which, like the first, has 5 ammonia molecules in the first coordination sphere. But the first is a chloride salt, the second is a sulfate salt. Now then, these two formulas tell us that isomers are different compounds, but share what property? They have exactly the same, what? Composition, you betcha. Isomers. Different compounds. but have same composition. Did you talk at all about any isomers in Chemistry 2045? I'm asking. Were you asked to consider any isomers at all in Chemistry 2045 laboratory? There's the dirty question. Because I know damn well you were. Because this is important stuff, and that's why I put it in there. So take note. These two compounds, each of which contain octahedral complexes of cobalt, in what oxidation state? What's the oxidation state for cobalt in these materials? What is it? Look at the formulas. What's the oxidation state of cobalt? +3. Right? Hey, in this compound, I got a sulfate ion which is -2 and a chloride ion which is -1. Well, all compounds are neutral, so the oxidation state of cobalt's got to be +3 since the ammonia molecules have 0 oxidation states. They're molecules. Now then, Q. How distinguish between these compounds? By methods of CHM2O46L. How about that? I'm going to put you in a laboratory, 46 laboratory. Check you back in. And I'm going to give you compound 1 or compound 2, but I'm not going to tell you which one. And I'm going to tell you, by the methods about which you have learned in 46 laboratory, you got to tell me whether or not I issued you a sample of compound 1 or compound 2, meaning your final grade will be A or 0. You got to get it right to get the A, and of course you know what you get if you get it wrong. What are you going to do? And of course you have to provide the confirmational evidence. I could care less about your opinion. You might make the right vote. I don't give a damn. What are you going to do? You did this work this term. What are you going to do? It follows directly from what you did in lab plus what we've talked about today. What are you going to do? Besides scream and holler and shout bloody murder.
Would you try to form a precipitate one of those?
Which one?
Chloride. That's what I would do.
So what are you going to do?
I would do the silver test. Right?
Silver test. You're going to make a water solution of the compound. And you're going to treat this water solution with silver nitrate reagent. And if you get ready precipitation of chloride ion, you got this one, don't you? And if you don't get ready precipitation of chloride ion, what now would you treat the solution with? Because I don't like making decisions on negative results. What did you say? Barium nitrate solution. Because if you got this compound, you're going to get ready precipitation of what? Sulfate ion. Barium sulfate. You betcha. That's all there is to it. Now, why are these called isomers? Because if I take and place this in water solution, particularly if it is a sulfate ion containing solution, I will find, if it's a chloride ion containing solution, I'll find that this will convert with this. Similarly, on standing a water solution of this, will convert to this. And after a while, I'll have a mix of these complexes in the same solution. Some of which contain sulfate ion coordinated, other of which contain chloride ion coordinated. But you won't find the ammonia molecules leaving the complex. They're too strong ligands. They won't leave the complex. Pick it up from this point tomorrow.